Psypher.
Check, check, check. Okay, so wait a minute. Let me start up here. I'll start a timer. I think we can start now. Yeah? All right. Okay, so hi. I'm Ashwin Shankerji. I'm from Psypher Interactive. Yeah, some of my friends are over there. I am the head of R&D over there, for the lack of a better term. It's more like head of ridiculous and devious code, a lot of head scratching. So yeah, we are making Cosmic Race. It's a car racing game that we have been making for quite a long time, and it's progressing very, very slowly. But in between all of that, we've had a lot of findings which we'd like to share and help people who are probably going through the same hell of the journey. So I've started back in 2013 making video games. I went to a college and met all my friends there who were all in a similar boat of self-discovery about video games. And yeah, so mostly my why would be I'm quite passionate about this. So this is purely passion driven. And it takes a lot of time kind of to stick to one problem and have that itch to see it through and finish it basically. And for the longest time, back then I started back in 2013. So multiplayer games were still there, but not everywhere. And now I guess we have awesome internet, more or less, and we can all play video games even in a phone or a computer and pretty much everywhere. And now me and my friends we are making a PC game, so that requires a lot of networking. And we are making a car racing game, which is a vehicular combat sort of a game. And we're going to be talking about how to, make your cars in the game feel better so that it looks nice and the players feel more or less satisfied, right? Because otherwise people are going to be like, not good. So I hope whatever that I'm going to share over here is going to come out well and you can put in into your game. There's a lot of code. I hope that wouldn't bore you, but it is there. You can screenshot and see how that goes once you try to implement it. Um, so yeah, essentially we have a racing game, right? And they weaponize speed, so to speak. So, and networks never is on your side. They try to do the opposite, as you can see. And we have to kind of shake hands, somewhere, it needs to work in perfect sync so that it gives you the illusion that everything is all right and you are playing a normal game, which is not hacked, so to speak. So our goal, for this particular game is to have some sort of a very good, smooth, the car should feel smooth and it should feel fair since we are in a multiplayer thing, right? And of course, our multiplayer game has bandwidth, so we shouldn't be sending a lot of data and kind of make our CEOs very unhappy with the data bills. So that's also one of the things that we should keep in mind when making a game. And as we all know, the internet can't be trusted. They always put you in for a toss. The latencies can widely vary from anywhere between 20 milliseconds to like 200 milliseconds, which wouldn't be the best thing for a video game or a racing game because that might not look all good. So the jitter is where that feeling that, is that frame rate or what's happening around, right? And we have a lot of packet loss. I mean, it's a multiplayer game after all, and it's a car racing game. It's not turn-based, so we need to be quite real-time about a lot of these things. So, and there's something called reordering, which I will get to in proper depth later. So before I get to all of these things, I'll show you how it kind of looked before. You'll have to look for it particularly, but look at the cars, the opponent cars, right? So I'm going to play the video next. And you can sort of see in this video the cars around you, they kind of jitter and move front and back, front and back. This not of a sync or a smooth feel is not there. And I'm going to play that video maybe again. And this time around, you can see that as soon as the game started, the other cars took a few seconds to kind of start along. All of these goes to say that there's a lot of lag. And this used to be our old video that we had long ago. And this lag is what makes everybody's life hell. No one likes lag. So, and then up the next video that we have is something from our newer generation of games, or the tech that we have. You can see one small frame skip, that's not part of the game. I lost a whole second there. But the idea is to give a smoother than earlier visual, right? You can immediately see that the cars started all together, and they're more or less smooth, and there's not like some sort of a jitter, right? So doing this was excruciatingly painful. It took a lot of time, lot of scratching heads. And I thought I'll share some of that findings to whoever else is in the same boat as I am, or will be in the future when you, or if and when you choose to do this sort of programming task. So yeah, this is going to be slightly technical. We're just going to show a lot of code that we have from the game directly so that you can see we are not lying. But it's useful to get these real life code examples. We have the game down in our booth. You should check it out just to see if what I said makes sense. You can drag and drop, take pictures, put this code. You can see the effects today, or at least it's a good place for you to start, you know. So our roadmap is more like, I'll walk you through the system architecture that we have, and how we buffer all these different packets, and some of the prediction techniques that we use in the game, and how we adapt for latency, which is the killer, and our real world implementation. So that's probably going to be the code snippets that we've used in the game. The game itself is live down in our booth, so come around, say hi. We have made this game in Unity, and we use netcode for games. We use the relay architecture and the lobby service. So we have a dependency on Unity's UGS, Unity Game Services. But that shouldn't matter. I mean, that's what we use as a solution. But the techniques that I'm going to talk about here, you can use it anywhere else, however you wish in your games. I'm just going to put my timer back so that I don't know how long is. Yep. So yeah, we can start. I'll go on to the next one. All right. So just one moment. The notes have stopped updating. So yeah, we have the system architecture. So I'll walk you through that. Our system over here, we use Unity netcode for game objects and not entities. And it features owner authoritative physics. And that's more like we don't have a headless server. It's mostly coming in from all the players that are playing in-game. And one player is generally the host. But that doesn't necessarily mean that that player's laptop is the server. There's a central server, relay server, that relays these messages through, which is what we talk by this owner authority. So what owner does is, in Unity, we have different kinds of updates. We have fixed updates, we have late update, we have and normal update. So these all are different kinds of update loops where you can kind of get in, let's say, during the physics sync, we can get into a physics update. When it's about to render, we can cut into that using the normal update. And then there is a late update it's in the name, it's late. So before, just the last final update before you render everything else. So the owner simulates, in our game, what happens is we simulate whatever things, the physics or whatever that we need in fixed update. In the fixed update, we kind of make a packet which has, the position, the velocity, the rotation, and any other things, the angular velocity and the server time, that's the position of the cars at that particular instance. And then that server, that owner relays it to the server, or rather the host in the game. So if it's we have up to 8 players. So one of them, if 8 people are playing, one of them would be a host and the rest are all clients. So an owner sends it to uh, the host, and the host kind of gets all this information, sees if they're all good, and sends it across to all the other different clients who needs this packet. And the clients, what they do is they buffer the incoming data. So instead of getting these data just one by one and then immediately displaying it to the game, we kind of buffer it, put it all in some sort of a bag, and then we do, in the late update is where we kind of put it all together and show it to the user. And we use UDP packets. So in a networking game, there are different ways that you can send packets. We have TCP, which is head of the line. It's kind of blocking. So that protocol pretty much makes sure that you don't kind of uh, miss packets. You know, it has something called retransmission and all sorts of things. So if I send something, it kind of makes sure that that client receives it. So inherently, because of that, there is some sort of a lag because of all of the tech that goes on behind TCP, right? Because it needs to make sure that the client received it. If it has not received it, send it, and there's a bit of an overhead with that. As opposed to UDP, which is faster, and it's used for like uh, first come wins. You know, it just keeps firing it, and it doesn't matter if the packets kind of get lost in the ether. So the client gets all of this through a UDP buffer, and essentially it renders it after, you know, in a late update sort of a sort of essentially after the whole physics and the rendering is done, you know, just before the camera gets the movement. So the order goes like from the owner sends it via fixed update. It generates a whole set of packets, so to speak. We have velocity, angular velocity, rotation, and position, and everything. It goes to the host sends it back to all the clients. Clients kind of put it in a bag, and then it reads from that bag and puts it in order and buffers, and that's how the smooth visuals are created in this. So when I talk about how to send this data, if if you're using Unity, at least if using the UGS, there's something called network variables in that. These are variables that just get synced across different connected clients. And they can be used, but they're not that great. It's kind of verbose. So when I say that, they take up so much data. So if you were to send like a small position update, a position in Unity can be like a vector 3. So it's got X, Y, Z, all sorts of data associated with that. So if you're using floats, you know, you can get these numbers that are ridiculously big, which is fine for precision, but when you're in networking, every byte matters. So you should kind of want to put all of that kind of compact and precise so that you don't take up a lot of space. And these network variables were quite chatty. By that, I mean, they keep talking all the time, you know, because they're trying to sync across so many different clients. And you can't control how often this happens or when it happens or if it happens. So kind of using that is a bit of a headache. And they are hard to evolve. So by that, so when we are developing a game, you have instant ideas. You have things like, okay, I need to send position. And maybe you'd think, I need to send the rotation of the car so that the rotations can come out good. So when you start making these sort of decisions, the contract, so to speak, that is essentially what are the data bytes that I send. That keeps changing, right? And it's difficult when it keeps changing because you need to adapt for each of those changes, and many different changes have to be done for that. So then I came across protobuf. So that's something, a protocol that's developed by Google long ago to work in their data centers. And after which, once they have made enough dollars, they kind of released it to us general public. This has happened over the years, and they are in protobuf version 3. So what this essentially is, it's sort of like a data interchange format, kind of like, think of it like JSON XML. So, you know, you can use different tech. So what we've used is a protobuf, and what that offers is about 40 to 60% smaller size, because for the same, let's say for the same objects or for the same packets of data, like which has position, rotation, and any sort of bundle of data, what would happen with the previous, let's say if I use JSON to transmit or XML, it takes up a lot of space, and we need this to happen now, like, or yesterday, pretty fast. And that's not possible when you have a game and when you have network bills to pay. You need to kind of be very sure that, okay, I'm not sending a lot of data, and I should be able to send as minimum as possible so that everyone on the table feels happy. People who are paying the bills should also feel happy, and people who are playing the games should also feel happy about that. So protobufs lets us kind of achieve that, and we're not still fully happy. It is a journey, so this will change. But to begin with, our protobuf version sends about 70 bytes per tick. That's very, very less. And it can be lesser, but so far 70 bytes, we are happy with that. So our earlier version was about 180 bytes per tick. So using protobufs, we are able to get that, and this is at 60 hertz. So that just means 60 times a second we try to send this whole set of data across. So the lesser the bytes, the better. And yeah, so that's protobufs for you. I highly recommend everybody to use that. It's essentially you can pack it all to one single byte stream and send it across the network and hope the other side receives it. Yeah, so this is something called timeline, or rather, when we send all of this data from client A to client B, what would happen is these all clients that run on separate times, so everybody's got a notion of time on their systems. So we need to make sure that everybody is in the same frame of reference, right? So you don't want to look at a local time or anything. It needs to be a synchronized network time that is shared across all clients. So this was actually one of our biggest return of interest, so to speak, because once we fixed this, we made sure that we are stamping these packets with the same time. So if I am sending a packet, if I'm client 1, if I'm sending it across to the next person, client 2, I make sure that I stamp it in the same time using, let's say, using the same watch to kind of stamp that packet. So when a client 2 receives it, client 2 knows that, okay, this came in this time, and there is no contention to the time. Because in a network game, everybody is on a slow, sort of a different time because of obvious lags. It takes time for a packet or anything to reach from one spot to the other. If I throw a ball and toss it over to you guys, it does take a few milliseconds to reach you all. And that's essentially what happens through our line. So we need to kind of make sure that we use the same time when we deal with these things. So every packet, we call our packets, let's move data, and it's stamped to the network time. And that's what we use that across all our clients. And then again, when we do show it on a different client, we never show it for that exact same time. It's sort of like with vision, right? Even when you see things, you are kind of seeing things, let's say some 2 nanoseconds into the past, because it takes time for the light to reflect off the things and get it registered and you see. So essentially with video games too, you don't need to kind of show it at the same time. You can kind of render your thing kind of like 100 milliseconds, maybe 200 milliseconds. That's too much, but in a few milliseconds to the past, so that you have enough times to kind of get all the packets in and kind of smoothly display it. So that's what I mean by playback cursor. So we send a packet A, we send a packet B, and we kind of look back into the time a little bit, maybe 100 milliseconds, and interpolate between A and B packets. So that's what I mean by this. And then we have something, a buffering strategy. So like I mentioned before, all the clients kind of accumulate all of these packets in. So I have a bag, I get these packets from the internet, put it in, put it in, put it in. And essentially, I have a bag that's got a capacity of 128. So that kind of gives us good headroom. And why 128? So that's more like 2.1 seconds roughly of data, past data. So I keep my bag filled with data of the past 2.8 seconds of gameplay. And we are always rendering it kind of a few milliseconds behind. So that gives us enough headroom to kind of use this 2.1 or odd seconds of positional data, and we interpolate between each of that. So packet A and packet B, so it kind of interpolates sort of this way because it has all the required necessary data to do that. And in the game, we have a send rate of about 60 hertz. One might think that's too much. Maybe we will reduce it once if our server costs go up. But for our purposes, 60 hertz does a very good job because we are sending it at that many times a second. You know, we send packet A, packet B, packet C, and it keeps happening very fast. So the more the better, more the merrier. And yeah, it's a circular buffer. So we don't, these are things happening in real time and it needs to be smooth. We don't want to spend a lot of time managing memory in the game because we have other things to do in the game. So we need to be very careful with how we handle all that memory. So a circular buffer will help you kind of with all of these things. So yeah, this is something that you can use, a small snippet of code that you can screenshot. This is essentially what we use straight from the game. The owner kind of sends all of these snapshots unreliability. That just means I don't care. I'm just going to throw it out. You receive it, that's your thing. But I'm just going to keep firing it as fast as I can, and you should just get it. And I hope that you get it. So, and for state, actually, what would happen is I don't need to wait to know whether or not my packet has reached you all. So the latest always wins. So I keep throwing packets, and there's somebody trying to catch all these packets. And it can so happen that the same packet can come twice, thrice. You know? So we need to kind of deduplicate what is being received. So make sure that all of the packets that I'm receiving across all my clients are unique. And we account for lag. So that's what I mean by the half RTT, right? And essentially, once the owner sends it to the server gets all the packets, server sends it to all the other connected players. And essentially we pass it, you know, we check for the ping and we kind of accommodate the time that it takes for somebody to send a packet, right? I'm the owner, I send it to the server, it takes X amount of time. Server gets that packet, sends it across other clients. So I need to account for the time that it took for the first owner also, you know, to kind of have sent the packet back into the server. So this is essentially the design that we use, you know, this piece of code. As you can see on top, you have the unreliable RPC delivery. So that just shows we're using UDP. And the same from the client. So they receive it and they kind of keep it to the buffer. And yeah, of course, the protobuf is small. So 70 bytes just keeps coming and you're easy to manage that. And yeah, after this, we get to the part where we interpolate. So that's where I would say the magic happens. We have a bag full of packets that I've received from my owner client. And the point is to kind of interpolate it pretty well across these packets. So we have snapshots essentially before, after, and A, B, C. And we kind of take all of that and use some of these this set of code to kind of interpolate between all of that. So essentially, I find a packet index. So that just means if this is the current time, I kind of want to simulate it 100 milliseconds or something to the past. So I choose that packet from my bag of packets. And I find a packet B. So that's just essentially the next packet right after packet A. And I find the time that it took between packet A and packet B. We use that and we get our interpolation factor. So we calculate that interpolation factor, use unclamped lerp to kind of find the final position. So if that's packet A and packet B, I find a position between that, taking in account of, let's say, the time that is taken between all of these packets. We do the same with the rotation. We use spherical rotation essentially. It's a smooth rotation blending. Cars kind of drift and spin, right? So a linear quaternion interpolation, that would cause some weird things that you don't want. You can try and see weird things happen to you until you switch to a spherical sort of an rotation. The same goes for interpolation between packets, the positions. They are linearly interpolated. And then we do some estimation for the final velocity. So this is essentially the same thing, you know, packet B minus packet A divided by the time that it took between packet A and B. And that gives us all of this jargon. A programmer would use all of this and goes to the next one, interpolation. So I've spoken about, that is extrapolation, sorry. I spoke about interpolation, that's essentially kind of going back into time. But it might just so happen that I receive so many packets, but sometimes, because internet's not your friend, it might just not send you any more packets. You do not have packets to deal with. So you have to do some more magic. That's extrapolation for you. So kind of try to predict the future. So in case these packets don't arrive, do not trust the packets ever. We get to this extrapolation part, right? So we calculate how far ahead that I might want to reliably predict. Take that some time ahead, maybe 200 milliseconds or 250 milliseconds into the future. Good, dangerous, but good. You calculate your acceleration, you calculate your final position. When I try to get this equation out, I used an LLM. They're great tools. You should always question and try to learn more from the LLMs, because it's sort of like if you have a senior developer or someone senior than you, you might sometimes find it shy or difficult to go ask for help and ask ridiculous questions from time to time. An LLM doesn't care, so you can keep asking it questions, give it dumb questions, all sorts of assumptions that you may have. You can refine yourself into a very good sort of equation. But that equation is what we've all essentially learned in school, right? Like that velocity into time plus half AT square. We've all used that in 12th standard, 11th standard, I think, 10th standard, even younger than that. So that's essentially the equation that we use to kind of see into the future, right? And we have a rotation and final velocity calculation with all of this. So essentially, we have extrapolated ourselves into the future. But the task is not over there. The latency kind of greatly varies. So you need to be very careful with that. You can try different numbers. After all, a game of putting these magic numbers and hoping for the best. So once all of this is done, right, you need to have essentially a good way to measure latency. And latency, at least for this sort of a thing, you need to account for the fact that a client sends it to the server, a server sends it back to across all the clients. So there are a couple of different pings, or so to speak, the latency that you have to calculate. The owner's half RTT. RTT is round trip time. And we kind of smooth it over 50 samples. So don't just use the latest ping. Keep it, you know, I receive a ping, put it in a bag, and kind of average it over, let's say, 50 samples. That's just my number. You can use 10 samples, 20 samples, anything that, however it works for you. And we kind of map to the delays. You know, I interpolate between 80 to 140 milliseconds. That is kind of 80 to 140 milliseconds into the past. And extrapolate kind of to 60 to 90 milliseconds into the future. That's more or less good for you. And then we get to our late update. This is where we apply all of these calculations and put it to the final positions, right? Because you don't want to directly apply all of those final positions and final vector directly into the rigid body, the physics of the car. So over there also, you kind of lerp it, right? You lerp and slurp. So that's all what you do to get anything that's smooth. Never use these values directly. You use at least for our game, we've used late update and kind of lerp all of this final positions. And of course, the bandwidth optimization. So in a racing game, that it can just so happen that a car is just standing still. You don't want to be keep sending the same packets of 000 position or whatever again and again and again, because the car has not moved, right? So once our system detects that there is no movement or essential movement, don't need to spend time sending the same packets again and again. So over there we can see that it sends only when there is some significant change. So once I start moving, I know that, okay, there is some movement and maybe I should start sending this data across. So I've used some sort of a small delta. So if I've moved, let's say 1 centimeter in a video game world, that's kind of good. And then I can start sending across all of these packets. And this is the final bit, the smoothing and the visual polish. What I had mentioned essentially, we do all of this to finally calculate the final position and the velocity and the rotation. We kind of slurp it across some delta. We use the final position and the final rotation, final velocity, and for the visual fidelity. So far I've spoken about just sending a car, so that's just position and rotation, velocity. But then we forget that it's a car racing game, so we have wheels in the game, right? For the longest time, we did not realize as a team that our network cars had just wheels that are sunk to the ground, right? There was no movement to the wheels were just kind of static, and the cars were just floating around, so to speak. So for the next level of visual fidelity, right? We do the wheels, how do I say, the wheel position separately using raycasting and whatever on the client again. So the wheels kind of look to the ground and detect where the ground is and position itself so that the proper positioning can be done. And then we do our VFX and the SFX. So somebody does a nitrous or presses brake, all of those particle systems and everything. All of this is done again on the client. I use separate recasts for suspension so that there is a feeling that there is a wheel that is essentially being simulated. And then we get to the gravity part. Don't do gravity. Don't simulate your clients. I mean, don't simulate your network cars with physics because the owner controls it. And this is the kind of a small cheat sheet that we use. These are the values that we use in our game. I hope my friends are not mad. We are giving away our small secrets. But this is quite useful. I guess everybody can start with these numbers and get to work. And it will help you, right? That's about it. And yeah, we've reached our conclusion. So I would say keep using the same time, never use different times. Always use the network time, which is an authoritative time. Everybody should know what time it is all at the same time. You can use protobuf packets, small packets, and you can make it into a byte stream, more or less, smaller size, bandwidth is good. People paying the bills will be happy. And you would also be a little happier than earlier, I guess, with protobuf. It's quite good. Then we have to realize that all of these things are quite real time. This is pretty computationally expensive. And you should make sure that you're not just ballooning your bandwidth or just initializing things and using lists and all sorts of things. Lists are good, but not in hot paths. So things like updates and fixed updates, these things get called quite often very fast. So kind of make sure that you can pre-allocate the memory, right? And then you know how much memory you'd want in advance. And use that and play with that. So never kind of go and balloon yourself out of memory. And of course, the right size matters, right? So you should know your numbers. How many times am I sending these packets across? 60 times? Good. Small memory buffer, because we have a lot of bots in the game sometimes if you don't have enough players. And these bots take up a lot of memory if you're kind of using up all of this data structures that might not do well for you. So make sure that you kind of stay within your memory budgets. Always lerp and slurp. It's a good thing to keep in mind. Do not apply values to the final thing ever. Just lerp it if you're just simulating it. And think about the bandwidth because it will matter one day. Yeah, and that's about it. Thank you all. I hope this has made some sense. And I do not know if I have any more time.
Ashwin, actually, we have run out of time. So, guys, we are very sorry. It was a very interesting talk. But if you want to have any question answer session with Ashwin, you can always contact him offline. Thanks, Ashwin. Thanks
Thank
a lot.
you. Thank you all.
Round of applause for him.
Thank you.